Good morning, good afternoon, and good evening, everyone. Welcome to today's Ask the Expert webinar, Unveiling the Invisible, an introduction to Atom Probe Tomography. Our presenters and experts for today are Dr. Yimeng Chen, Senior Principal Scientist, and our moderator, Dr. Mike Salmon, Scientific Fellow. My name is Rena Samsu, and I am the Senior Marketing Manager assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of pre-submitted questions for today's event, we unfortunately will not be able to get to all of them during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to our first presenter for today, Dr. Mike Salmon. Mike, I think you're on mute, Mike.
Oh, thanks, Rena. Sorry about that. Welcome, everyone, and thank you for joining us today. My name is Mike Salmon, Scientific Fellow of Advanced Imaging at EAG. During this webinar on Atom Probe Tomography, or APT for short, Dr. Chen will be answering all of your APT-related questions, ranging from general operation to application-specific details, and then finish up with some explanations of the limitations and what are considered difficult applications for APT. Please feel free to submit additional questions throughout the webinar through the GoToMeeting app, and then during the presentation, as we will have an additional Q&A at the end of the webinar. Hopefully, we'll have time to address all your questions, but if not, we will reach out to you individually afterwards. Before I turn things back over to Dr. Chen and APT, let's go over a little background about our company, Eurofins EAG. So Eurofins is a global leader in testing with more than 58,000 employees, 900 laboratories in 54 different countries. Eurofins EAG is a division of Eurofins specializing in materials testing with over 40 years experience. We have more than 1,000 employees and 20+ laboratory facilities all over the world, supporting 5,000 clients with more than 2,500 different types of testing equipment. This is a chart you may have seen before called the SMART chart. It's a useful tool to help you determine the proper method for your analytical needs. You can find a copy of this online at the QR code in the bottom right, and you can even get your own poster-sized version of this chart for your lab. SMART is an acronym for Spectroscopy Microscopy Analytical Resolution Tool, and it shows the techniques we have available here at EAG, color-coded and plotted on the chart according to the spot size and the detection limits. The x-axis shows the range of spot sizes from 1 centimeter at the right down to 1 angstrom at the far left, while the y-axis shows concentrations either in atoms per cubic centimeter at the left or in atomic concentrations at the right that range from 100% to 10 parts per trillion. The blank area on the lower left corner corresponds to the physical limit of the chemical analysis according to the sampling size. And in this chart, APT is located at the upper left corner. It combines both the imaging and chemical analysis capabilities for sub-nanometer spatial resolution and the parts per million level sensitivity approaching the physical limit. With the 3 techniques occupying the upper left corner of the chart, APT is suited for bridging the gap between TEM and SIMS in both terms of resolution and chemical sensitivity. So without further ado, I'm going to turn things over to Dr. Chen, and he's going to get to answering all your great questions on APT.
Hello, everyone. This is Yimeng Chen. I'm the Senior Principal Scientist on the Atom Probe at EAG. So thank you very much for taking your time to attend this webinar. We received over 200 pre-submitted questions that covers a wide range of topics So we'll get these questions categorized and answered in groups. And since many of you are new to the technique, so I will start with the basic of Atom Probe, showing the working principle of Atom Probe. Like some of you ask the difference between APT and AFM, so you see there are two different techniques. So let's first start with how Atom Probe works. So APT stands for Atom Probe Tomography, that is a point projection microscopy that combines single ion detection and 3D tomography capability. And the schematic shown here consists the main component in Atom Probe instrument. That on the left is the needle-shaped specimen with very sharp end radius between 20 to 100 nanometers. And in the middle is the conical hollow local electrode for field enhancement. And to the right is the position-sensitive detector for ion detection that typically combined with 36 to 80% detector efficiency depending on the model. So the technique relies on the process of field ionization under extremely high electrostatic field in order from 10 to 50 volts per nanometers. And Atom Probe is carried out inside ultra-high vacuum environment in the low E-11 torr. Also, during the analysis, the specimen will be kept at a cryogenic temperature, typically between 20 to 100 Kelvin, to minimize thermal vibration of the surface atoms to improve the spatial resolution. So under the high electric field, the surface atoms on the specimen will be ionized and feel evaporated, occurring in a controlled manner with application of either a pulse voltage or laser pulsing. So the field evaporated ions will be projected to the detector and they will be positively charged. So the ions will gain electric potential energy between the high voltage tip to the grounded detector. And after passing the local electrode, the ions are considered traveling at a constant velocity towards the detector. Upon arrival, each impact position on the position-sensitive detector will result in the detection of the impact position on the detector coordinate as well as time of flight that takes the ions between the specimen to the detector. And the identification of ions will be realized through the time of flight spectrometry. So although the exact mechanism of field evaporation is unclear, but is commonly described as a thermally activated process. So the diagram shown here is the potential energy of an atom's on conductive surface. So the blue curve describes the potential energy of an atom as a function of distance. So without the presence of field, it requires energy Q0 to remove atoms from the specimen. And in the ionic state, the energy barrier will be further reduced under the application of a positive field. The energy will be greatly reduced, and the diagram will be pushed downward, reducing the energy barrier to a much smaller value of QF. So as shown in the equation below, this is a possibility of field evaporation that can be described in the exponential function where QF is the barrier height, T is the temperature, and K is the Boltzmann constant. So this equation illustrates that the possibility of field evaporation is positively related to the increase of the field and the increase of the temperature. So you may wonder what will be the critical field for ionization for certain elements. So the table to the right shows the calibrated field at 77 Kelvin based on the image hump model proposed by Tizong in 1978. So in general, high melting point elements like tungsten requires extremely high electric field, over 50 volts per nanometer to field evaporate. On the other hand, the lower melting point material like aluminum requires a lower field. For example, for aluminum, it's 19 volts per nanometer. And silicon is a well-studied material with atom probe that requires a moderate field around 30 volts per nanometer. So since the field evaporation is a probabilistic concept, the different charge state can coexist in the process of field evaporation. So that's why if you pay attention to the table, you see 3 different values that represent the field strengths to generate the singly charged ions, doubly charged ions, and triply charged ions. So the combination of different charge state often relates to the strength of the field that usually can be used as an indicator for matching the condition or estimating the field that the ions were actually evaporated. So the position sensitive detector records the impact position on the detector space, and they will be later converted into the specimen space through a simple back projection algorithm to obtain the lateral coordinates. So in this process, the detector space coordinate xd, yd will be in millimeter space will be converted into the xy in nanometer space. And the depth coordinate is calculated from the sequence of arrival. And in this calculation will be involving several parameters like the magnification, tip radius, angular field of view, and detector efficiency, and atomic volume. And this process of converting the position, the coordinate on the detector base to the specimen base is called reconstruction. And identification of ions is realized through the mass-to-charge ratio that is deduced through the time of flight spectrometry. So the underlying mechanism is expressed as E equals minus NeV, where E is the electric potential energy and N is the charge of the ion, E is elementary charge, V is the voltage applied to the specimen. So in this concept, following the energy conservation law, the electric energy will be fully converted to kinetic energy expressed as 1/2 m/v squared, where v is the velocity of the ions traveling between the specimen to the detector. So the velocity term v can be replaced with L/T, where L is the distance between the specimen to the L is the actual distance traveled for the ions, and T is the time of flight. So from this equation, the mass-to-charge ratio can be expressed or calculated by calculating the time of flight, which is the only unknown in this equation. So we obtain a mass-to-charge mass spectrum that from where we can utilize the mass-to-charge ratio to identify different type of ions based on their mass-to-charge. So combining the ion identity with their relative position in the specimen, we obtain atom probe data for elemental distribution. And atom probe is a destructive analysis that specimens are actually consumed during the analysis. Like the top one is the initial tip, the apex of the tip, and we consume certain amount of material from the core of the specimen and ending up with a larger radius tip. So by collecting the ions from the evaporated ions with identification through mass-to-charge spectrum and their location from the 3D reconstruction method, we obtain this type of atom probe data. So like this one is showing the quantum well structure in an LED device, showing the magnesium doped region on the top and the indium enriched quantum well. And the typical size of the analysis is in the order of hundreds of nanometers. And there will be a 3D-dimensional illustration of the ion distribution in 3D. So this will be an introduction, and we also received a lot of questions asking about how the atom probe can be compared to other instruments like SIMS or TEM or what kind of spatial resolution or detector or detection efficiency for Atom Probe. So since, as what Mike introduced earlier in the introduction, APT, SIMS, and Atom Probe have some similarities in the application space. So let's compare them side by side. So this table summarizes the difference between the three techniques. So the first one is the SIMS, that is recognized as the most sensitive elemental and isotopic analysis that can achieve part per billion sensitivity. And with the dynamic SIM mode, combines with high chemical sensitivity with nanometer depth resolution, and the typical area it analyzed is 10 by 10 micrometer squared. That's the and the SIMS relies on the bombardment of the primary beam to generate the secondary beam, and they can analyze this size of a volume. And this is the initially a one-dimensional technique, and it requires calibration standard to achieve quantitative measurement. And also, as mentioned, it's also destructive analysis. So in comparison, the analytical TEM combined with energy dispersive spectrometry EDS can best achieve like atomic percentage sensitivity. And the EOS for the electron energy loss spectrometry can achieve best achieve 500 ppm resolution chemical sensitivity. And for the imaging resolution, TEM or STM can achieve Armstrong level imaging resolution with aberration corrected instruments. And this is a two-dimensional imaging technique, can image area as large as 10 by 10 micrometer squared. And for the EDS and the EOS analysis, it also requires calibration standard to achieve quantitative, semi-quantitative analysis. And as the imaging technique, TM is not destructive, and the same sample can be imaged or analyzed multiple times. So in comparison, Atom Probe provides true three-dimensional information with a typical analysis of hundreds of nanometer range, and it combines a high chemical sensitivity in the ppm level with atomic resolution for metallic sample and sub-nanometer resolution for oxide. And usually the spatial resolution in the depth direction is better than the lateral direction. It utilizes the time of flight mass spectrometry, and it measured all the incoming ions with theoretically equal sensitivity. So in general, it doesn't require calibration standard for the chemical quantification. And in the picture below, gave you a flavor of the strengths of each technique. Like SIMS provides the best chemical sensitivity in depth profiling, but if you want to analyze structure with a complex three-dimensional structure, the SIMS doesn't have the necessary spatial resolution to resolve the small features. On the other hand, the TEM can be used as imaging, and combined with the EOS or EDS, it can map out the different elements in the structure, like this FinFET structure. And Atom Probe provides you three-dimensional information in the similar structure, and has the high spatial resolution and high chemical sensitivity. So later on, we will show you more examples on the application. So we also received questions about how the Atom Probe samples are prepared, and what kind of calibration we do on our instrument, and also what kind of a restriction we can have on the sample preparation, and what kind of a service we provide. So the instrument we have is the LEAP 5000 XR system. Then the LEAP stands for Local Electrode Atom Probe. That is unique to the Atom Probe instrument. And the tool offers great reliability with high throughput. And the instrument we have is combined with energy compensation reflection design, and it provides the best mass driving power in the market. Our instrument have around 50% detector efficiency, means we detect half of the ions arriving at the detector. And we also offer comprehensive service on coating the specimen, deprocessing, high-level set-specific sample preparation, and we also offer from basic to advanced data analysis with detailed reporting. And I can say with the EAG, we are committed to providing the best quality atom probe data for your analytical needs. So about sample preparation, this is the general step for the conversion of sample preparation in the top-down orientation. So first, we will define the region of interest on the surface, and this is the SEM image. And we deposit a deposition layer that to prevent sample from FIB damage during the subsequent milling steps. Then we do a trench cut to isolate the wedge-shaped region for the lift out. Then later, this wedge bar will be lifted out and mounted to a substrate for the milling process. So up to this point, the process is very similar to TM sample preparation, but instead of preparing thin lamella specimen, we apply annular milling to sharpen the specimen into needle-shaped shape, and the end radius need to be smaller than 100 nanometers to generate enough electric field required for field ionization. So we also capable of doing advanced sample preparation like targeting green boundaries, and we can do direct lift out for powder specimen, and we also can do different rotations like cross section or backside that are usually needed for the device sample by reorientating the structure relative to the direction of evaporation. About our instrument, we take great care of our instrument. We perform weekly calibration to ensure the specimen, the instrument is at the best condition. Like this is the spout site we collected over years, showing we have a well calibrated spout sites under 400 nanometers, and we do laser focus calibration on every specimen. And for certain applications like gallium nitride, we know we have some nitrogen deficiency, so we plot the measured composition between gallium and the nitrogen as a function of a laser, helping us to determine what will be a good laser pulse energy to use for certain applications. We also measure a lot of silicon-based materials that we put intensive effort by plotting the different combinations between different laser pulse energy and effective laser pulse fraction. So this will be helpful if you want to matching the result between laser pulsing run to the voltage pulsing run to finding out what will be the same effective pulse fraction to a certain laser pulse energy. The silicon charge ratio will be the indication for matching run conditions. As mentioned previously, the charge ratio represent the strength of the field. So if you have analyzed a sample before on other instrument, we can match the condition by assessing the silicon charge ratio, choosing the right condition, the laser pulse energy on our instrument. Also, we try to run the specimen with the lowest possible laser pulse energy to improve the spatial resolution, but also it has some correlation with the background level need to be understood. So we try to improve the spatial resolution, the mass spectrum quality, but we also don't want to introduce too much background in the dataset. We also has a very strict rule for the pumping time to ensure the best vacuum quality. Usually we set the sample in the chamber at least 4 hours in the low log and 4 hours in the buffer. so it won't suffer from the higher background due to the poor vacuum quality. We are also very grateful for the good service from Kamika in the effort of reducing the downtime for our instrument. So now let's take a look at some real applications. We received several questions about where the Atom Probe has been used, what is the sort of the volume Atom Probe can analyze. It actually depends on the type of material, and there are many interests in measuring the heterojunction structure with thin layers. So from now, I'm going to show you 5 examples. So I intentionally skipped application for metrology applications because they're due to the abundance of sample examples available in the literature. So instead, I would like to focus on the analysis for commercial LED, a multi-layer ceramic capacitor, dopant analysis in silicon, a commercial 22 nanometer FinFET structure, and the dislocation analysis for the 3.5 device. So these are considered a more advanced application for Atom Probe. So the first one will be a commercial LED that we purchased from the market and depackaged at EAG. So the sample contains many stacks of heterojunction layers with different functionalities. And to the right is the typical mass spectrum we obtained from LED sample. So you can see we have ions evaporated as singly charged ions for indium, gallium, and we also, at the same time, in the mass spectrum, we also detect doubly charged ions or triply charged ions. And we also obtain molecular ions like the nitrogen-2 singly charged, nitrogen-3 singly charged, or even combining with the gallium. So these are the molecular ions formed during the field ionization process. So the dataset has excellent mass roving power with low background, and we can analyze and quantitatively measure the low concentration elements like magnesium and aluminum in the sample. So we first took a look at the sample in STEM, and this is the cross-section image from this layered structure. And this is a dark field image where the brighter region corresponds to the region with higher atomic number elements. Atom probe data was collected from the top-down orientation, and this data contains 50 million ions that covers over 600 nanometer in length. So you can see for this type of material, you can collect pretty long data set. And we have atom probe data from crossing many of the different layers. And in the data, the different type of elements are color-coded for aluminum in blue, gallium in orange, indium in purple or red, darker red. So we are interested in several key components in this structure. The first one will be the pGaN region on the top that is doped with magnesium. We can see the magnesium is not uniformly distributed, but forming clusters. So using Atom Probe, we can measure the number density of the clusters and the composition of these nano-sized clusters that will be beyond the detection limit for TM to observe or quantitatively measure. And in the middle, we have the quantum well layers that we have a STEM imaging showing 3 layers. The first 2 are combined with the brighter layer followed by a lighter region. And the Atom Probe data obtained from this region confirm that there are actually indium layers of 10% followed by another layer of 5% indium concentration layer. And each layer is about 5 nanometer in thickness, and we have 3 groups of them, and composition can be obtained by Atom Probe. And further down in the structure, we have the superlattice that contains in average 1% of indium and the layer thickness is around 1 nanometers. So this example demonstrates for the 3-5 materials, we can obtain the key component like the pGaN, quantum well, and superlattice. And for gallium nitride material, we usually obtain relatively large specimen over hundreds of nanometers. So let's move on to the second study. And now we are going to focus on dielectric material. This is actually oxide. And we are also taking a step forward, showing correlative analysis with TEM. So let's first talk about why we want to do correlative analysis with TEM. So APT and TEM are actually two very complementary technique, because the size of atom probe specimen is already sufficiently thin for direct observation with 200 keV TEM. And electron microscopy offers many details on crystal structure, precise dimension measurement, and on the other hand, Atom Probe provides precise measurement on the chemical composition from a small volume, from localized space. So combining the two techniques, we can particularly beneficial for Atom Probe for improving the reconstruction accuracy, obtaining crystallographic information or green boundary misorientation information, and we can also we are also going to show you using TEM imaging to pinpoint targeting a particular feature for Atom Probe analysis. So in this work, the sample we choose is MLCC. It's a multi-layer ceramic capacitor. This kind of a capacitor is used in power stabilization, signal processing, wireless communication. And this is actually the best product in the market we purchased. It is the COG grade class 1 dielectric MLCC that has good performance in a wide range of temperature and voltage and frequencies. So in the smartphone, especially those with 5G wideband communication, a smartphone can contain 1,000 to 2,000 MLCC devices. And you can see they come with a very compact size as comparing to the size of finger. So in such small volume, it actually contains very complex structure that is made of alternative layers of ceramic body and electrode. So commonly used materials for the ceramic body are perovskite materials such as barium titanate, and the electrode is usually made of some pure metals. So the sample we had purchased by EAG, and we carefully mounted and deprocessed on the cross-section. And this is a SEM image observed in cross-section, where these thin bright lines are the 2 micrometer thick electrodes and embedded in a huge body of ceramic. It's not very clear, but you can see there are some black dots cutting or dividing the electrode. And these black dots are actually the secondary phase of a ceramic in the body, often observed near the electrode. So we took a TEM specimen in the same orientation in the cross-section, targeting the interface between the electrode and ceramic body, including the secondary ceramic phase. So you can see the body of the ceramic are polycrystalline with grain size between 1.5 to 2 micrometers. And the secondary ceramic phase has a different contrast in TEM. And with EOS, with the EDS mapping, we determined the local electrode is made of pure nickel, and the main ceramic body contains higher amount of zirconium, and the secondary phase contains silicon and higher amount of strontium. So there are two different phases in the ceramic body. and we would like to analyze the interface or grain boundary for this sample. So to do that, you can see the number density of the secondary phase is not great. So you can imagine if we randomly pick a location from this sample, we are not likely to include the secondary phase. So we invented a new protocol for sample preparation that involves converting a TM specimen into atom probe. So these are the wedge-shaped TM specimen mounted on a silicon grid. And these are the EOS mapping results. We're getting the nickel electrode on the top. We have the secondary phase enriched in strontium, manganese, and calcium in the middle. And on the bottom is the primary phase. So we want to target a very specific region in this sample at the interface. So we can see there's the V-shaped interface that will inform us we have the interface between the primary phase to the secondary phase, and very likely at the end of the V, there's the green boundary, like we can image from the shape. So this is the feature that embedded in the specimen that would be hard for the traditional sample preparation to target. And with imaging the sample with TEM using EDS, we can observe the feature and target the region for atom probe. So to do that, we have the sample mounted on silicon substrate, and we can see the location that we want to analyze, and we apply additional milling to deposit the sample and center the tip right on the bottom of the V. So by doing that, we convert a TM specimen into atom probe specimen with the region of interest centered in the apex. So using the same method, we can target the different regions like the interface between the electrode to the ceramic and the interface, the flat region between the two ceramics. So we can do a lot of things with this sample preparation protocol that allows us for precise targeting. So this is the data obtained from this region. This is actually a triple junction region between have 3 grains, 1 from the secondary phase and 2 from the primary phase. And in the data, we observed the secondary phase enriched in silicon, and the bottom is enriched in zirconium. We can do a lot of detailed analysis on this data set. So we can do 1D concentration profile, showing the distinct oxygen concentration from the secondary phase to the primary phase. And we can also analyze the minor elements, like we see close to 80% of manganese in the secondary phase and 1.7% of magnesium in the secondary phase. So it provides very detailed composition analysis from this structure. And we can also do more detailed analysis on the green boundaries or phase interfaces. Like these are the 2D contour map for aluminum, silicon, and manganese, that we can identify the boundary between the primary and the secondary phase contains about 0.8% aluminum. And on the bottom will be the interface, will be the green boundary between the primary phase that is also enriched in manganese, silicon, and some small amount of aluminum. So this detailed analysis provides a good visualization of the elemental distribution on such complex structure, and we can achieve quantitative measurement for phases or green boundaries. So now let's move on to the application for semiconductor industry. So we saw a lot of interest in the application for semiconductors, and regarding the dope analysis in silicon. So let's take a look at silicon phosphide, analysis on the silicon phosphide. So the sample we have contains a 30 nanometer thick epitaxial silicon phosphide on a silicon substrate. And in the map acquired in the top down, you can see we have a protective layer on the top. We have 5 nanometer thick native oxide on the surface. Then below that is the silicon phosphide region with phosphor showing in purple. We have a second type of the sample received a shallow implantation for antimony on the top surface, where the distribution of the antimony can be clearly observed as the blue dots in the reconstructed data. So these are essentially the same sample, but one with the silicon phosphide and one with the shallow implantation of antimony. So at EAG, we also performed a differential Hall effect metrology that confirms that higher dopant activity can be confirmed associated with the implantation of this small amount of antimony on the surface. So to get 1D concentration profile, we plotted the atomic density for phosphor and antimony as a function of depth. So the phosphor concentration is uniform in the first 30 nanometer on the surface, and we measured around 1.4 E21 atoms per cube centimeter for the phosphorus, and for the antimony concentration, it peaks at 2E20, about 3 nanometers from the surface. And in the 1D concentration profile, the detection limit we estimated is around 3E19 in the 1D profile using a 0.2 nanometer bin size. So that's the detection limit from the 1D concentration profile. And actually, if we use the entire data set, entire silicon phosphide region, we can achieve better detection efficiency by using more ions. That will be estimated to be the low E18 if we use the entire 30 nanometer of the silicon phosphide region. So you can see the detection limit is actually depends on the size of the data. The larger the size you have, the lower the detection limit you can achieve, and for dopant analysis. So we also wonder, there are also some questions about if the analysis direction will alter the dopant measurement. So to confirm that, we performed a top-down orientation and cross-section with the sample running along the layer, along the silicon phosphide, or in a backside orientation to confirm the phosphor concentration in different orientations. So in the plot, we put the cross-section data in green and backside data in blue. So you can see we get a very consistent measurement for the phosphor concentration in the silicon phosphide. So indicating the analysis is not biased by the direction of the analysis. And we also would like to estimate the accuracy of our measurement. So we measure the average composition in the plateau region in the silicon phosphide, and we estimate the average concentration of 1.4 E21 with roughly about plus minus 10% variation. And that is estimated from 13 measurements, including different capping material. So that will be probably representative accuracy for our measurement. So with the atomic percentage of phosphor, the error will be around 10%. So these are a blanket structure, and we also received a question about the dopant analysis in three-dimensional structure, like the real devices. So this is definitely more challenging and more complicated. And to do that, we did analysis on this 22 nanometer FinFET structure. That is the microchip we purchased from the market, and we deprocessed at EAG. So this is a 22 nanometer node that was first introduced probably over 14 years ago. So even the technology has been decades years old, but this kind of CPUs are still being used in the market for our electronic devices or computers, and also the FinFET structure technology, the architecture is still relevant to the current technology. So this is and in such structure, the difficulty comes from it combines many different materials with different electro property or require different field. Like we have the FinFET silicon, we have the metal gate wrapping on top, we have the source drain region that could be doped for the N-type or P-type regions. So we would like to demonstrate how Atom Probe can use to analyze the dopant concentration in this device. And this is the TM image showing a fin wrapped with a diamond-shaped region that's usually the silicon germanium region with boron doping. So such structure, you can imagine that such structure will be difficult for SIMS to analyze due to the limitation in spatial resolution, and for TEM, you may suffer from the averaging issue in the projection error by having the feature of analysis thinner than the thickness of the sample. So you'll be measuring not only the region of interest, but averaging through the thickness of the specimen. And very often, the dopant concentration will be too low for quantitatively measured by EDS or EOS. So this is indeed a very complicated structure, and we need to first understand the structure. So we take many cross-section cuts along the fins, and these are the sequential cuts at 30 nanometers interval. You can see the fins exposed to the cross-section. The number of fins is different from one cut to another, and the shape of the fin also varies, indicating it's cutting through a different type of structures in the FinFET. So using our extensive knowledge about the FinFET structure, we can identify the different components in this complicated structure. So here's taking an example of one of the image. So in this one, we can see the brighter region on the top that are the metal gate. So sorry, they're not the metal gate, they're the contacts. And the gray regions are metal gate, and the darker region on the bottom will be the shallow change isolation made of silicon oxide. We see number of fins, and we can clearly identify the type of fins. Like the first two are dummy fins, and the third one is the N-type, then followed by P-type, then the other continues in the inverted order. So we can clearly identify what type of fin structure we are looking at, and we would like to target that region for Atom Probe analysis. So we also took more TM image along the P-type region, and these are the P-type region. This is the stem image normal to the previous image, and you can see we have several repeats of the different structures, and we did the EOS analysis on this one that identified the brighter region on the top are tungsten. So these are the tungsten via approaching from the top, touching the top of the silicon germanium region that we can identify in the EDS. So we have 3 silicon germanium region in this portion, and between the tungsten contact to the SIGI, they also have a layer of titanium, which doesn't show great contrast in the image. There are also other elements in the EDS, like these 4 set of rectangular shapes regions are the gates. The gates has a center with the tungsten and the wrapped in aluminum, titanium. Then they have the hafnium that is from the high-K material wrapping on the fin. Yeah, so the region we would like to analyze will be the SiGe region, approximately 40 by 30 nanometer of size in the cross-section image. So we try to target the SiGe region and prepare needle-shaped specimen from here. So the movie you are seeing on the left is the STM tomography movie that we took from -70 to +70 degree swinging rotation at 1 degree interval. So you can see on the top is the FIB platinum protection, and the high atomic number region with the tungsten you're seeing as a white region in the dark field image. And you can see these very complex structures in the tip. So we can take a closer look at a stationary image. So this is an image taken at 0 degree, and you can see we have the tungsten on the top, and we have the fin in the middle. You can recognize the diamond-shaped SiGe region in the middle, wrapping on the fin, and you have this U-shaped region that is titanium region in the metal gate. For tilted view, we can see the tungsten actually shrink to a thin blade and touching right on top of the SiGe region, as shown in here. And the gate are shown as like arched doors with this shape. So we have many different components in the tip. We have the tungsten in the contact. We have the tungsten in the gate. We have the tinitride wrapping on the fin. We have the SiGe region, a small portion SiGe region, silicon oxide at the bottom. So even this tip already contains the SiGe, but it's not suited for Atom Probe because the radius is too big and there's too much of tungsten that will be hard to evaporate. So for Atom Probe, we further reduce the radius and remove the tungsten region as much as possible to get a similar tip radius, tip specimen, but with much smaller radius, around 30 nanometers. So for many times for Atom Probe, knowing the exact location of sample prepared is as valuable as the data set itself. And for this case, we have 3 SiGe regions that we intentionally targeted the one on site because there'd be more tungsten for the one in the middle. So the region we collected for Atom Probe will be at the SiGe next to the gate. And this is the data we obtained showing the silicon germanium on the left, and we have other component to the right, and we observed boron in this region. The mass spectrum quality is pretty good for these complex structures. We see different type of elements from light to heavy elements. We also clearly observed boron as singly charged and doubly charged ions in the mass spectrum. Oh, let me go back. And this should be a movie. Let me turn this one. So this will be the fin. Oh, I can't stop it. Sorry. Okay, I can't pause the beam, but pause the rotation. But this will be the back of the fin, and on each side we have aluminum-rich region represented with the light blue cathode surface, and the fin is wrapped in hafnium. We'll see the yellow dots. And we took a 10 nanometer thin slice on the bottom, showing the SiGe on the left, and metal contact, and high K with the hafnium oxide, and the fin in the vertical horizontal direction. So you can see that we actually suffering from some distortion from this region, that the SiGe region is compressed by the surrounding oxide, and the high K region is apparently enlarged due to their field difference. So for this kind of complicated materials, when we have materials with different evaporation field, the construction will be distorted. But nevertheless, we used 20% of germanium to isolate the SiGe region, and we estimate the boron concentration in this region to be 0.08 atomic percent. We also see some boron outside of the SiGe along the interface of the fin to the gate. And we took a 1D concentration profile across the fin, showing the fin is wrapped in hafnium oxide that also includes titanium oxide. And further out will be the titanium nitride, and will be in the aluminum. So the layers we confirmed with the Atom Probe is in general in good agreement with the TM observation, and we were able to identify or quantitatively measure the SiGe region contains 0.08% of boron in the SiGe. So now let's move on to our last example. And we received a lot of questions about analyzing defects. Some of them are related to the failure analysis, like the dislocation or defects can cause leakage current that is detrimental to the device performance. So for this one, we're just showing analysis of dislocation in a 3,5 material. So the sample we use is actually a commercial charger we had in the lab, and the charger was deprocessed to obtain this gallium nitride integrated circuits. And many often for the charging devices, the gallium nitride tips will be used for power supply. And the gallium nitride is large band gap material that has better thermal performance and higher power density compared to silicon devices. That's why they're used for high power applications. So the device was depackaged and mechanically polished down to the source drain region, where we see the gates and we have the source drain in the gallium nitride on the bottom. And we did TM observation using STEM that we confirm a very high density of dislocations in this gallium nitride. And the observation was done with 200 kV electron energy TM. And we were able to confirm their edge and screw type dislocations in this sample. So and from this one, we obtained the data from the dislocation-free region, showing the top at the metal contact is made of titanium nitride, and we have the p-GaN region doped with magnesium. We have the L-GaN on the bottom. And from the 1D concentration profile, we can identify their 130 ppm of magnesium in the p-GaN region. And we prepared a specimen from the dislocation. And with STEM, we determine the dislocation and carefully mark the dislocation with carbon deposition. And this very same dislocation was extracted and lifted out again and mounted to a special holder that is both suitable for TEM and Atom Probe. And this pillar view was imaged again to confirm the dislocation is in the middle. And with the two beam condition, we can confirm this is the screw type dislocation. And the Atom Probe data set was obtained from dislocation, showing a distinctive difference on the bottom of the algan. And this is the slice view of the atom distribution. We show a V defect on the bottom of the algan. So the exact mechanism of the formation is unclear, but our speculation is the V defect already exists on the substrate, and after the epitaxial growth of the aluminum of the algan, it somehow managed to have a flat interface on the top, and the growth continues in the vertical direction. And in the 2D contour map, we can see there's the flat interface on the top, but have a 20 nanometer penetration point on the bottom that causing aluminum leaking into the gallium nitride. And with the overlay, we did one deconcentration profile confirming the composition is clearly different on the flat region versus along the dislocation that shows the diffusion of aluminum and magnesium. This is overlay between the 2D contour map with the magnesium distribution, and outside of the dislocation in the gallium nitride, we not detected any magnesium or aluminum, but along the dislocation, we clearly see the magnesium and aluminum along the dislocation core. So this is again image, a video after spatial ranging processing to remove the noise of magnesium in the gallium nitride. Is showing the diffusion of magnesium from the pGaN region through the algan and into the gallium nitride bottom layer. It's quite impressive to see the diffusion behavior of dopants along this location. Of course, for Atom Probe, as any other technique, it also has its limitations. Like it will be hard to analyze softer materials, polymer materials, or liquid material requires special cryogenic apparatus for preparing liquid materials. There are also certain artifacts in quantifications or artifact in the reconstruction. So we don't have time to cover all of them, but we will reply your questions through email, answering some of the common artifacts we see in Atom Probe data. So thank you for your attention, and this will be the last slide of my presentation here. So we provided the introduction to the working principle of Atom Probe, and we show that we can do advanced sample preparation using STEM correlated analysis. And there are also some limitations with the technique that you need to be aware of. So for any questions or inquiries, please feel free to contact us for a detailed discussion. Thank you very much.
Wow, thank you so much, Ximeng, for such an enlightening presentation. We have just a little bit of time to address some of the great additional questions that came in during the presentation. So let me just get right to that. Let's see, the first one is, how do you avoid or minimize gallium fib damage for APT sample prep?
Oh, yes. Yeah, fib damage is very common for sample prepared by gallium fib. And it's very similar to what you have with the TM sample preparation. So as what I mentioned before, we first put a protective layer that have a good gallium stopping power. So that will prevent gallium implantation when the high current gallium beam was used for the trench cut or the lift out. And during the melting process, we tend to finish the last melting step with a lower energy gallium beam. So in general, we use 5 kV gallium beam that will give you roughly a 5 nanometer gallium implantation region based on the SHRIM calculation. And also we can use lower current, lower energy like a 2 kV or 500 volts. That's an option. And also remember that Atom Probe is a destructive analysis. So any damaged region on the surface will be first evaporated at the initial stage. So we can realize on the gallium concentration to exclude the region that has received gallium implantation and use the clean or pristine region later collected during the analysis.
Okay, great. Another question that came in was, you mentioned an artifact with peak overlap in your mass spectra. How do you avoid, or how do you deal with these overlaps? And then what kind of advice do you give to folks that are just starting out in APT?
Oh, yes, that's a great question. So because it's a mass spectrum spectrometry, so it determines the ion identity based on the mass to charge. So anytime you have an overlap in the mass to charge value, you will have ambiguity between how to range or identify a certain peak to associate with a certain type of elements. So first, you should collect data as the best quality in the mass spectrum, like improving the mass roving power. And to do that, you usually need to run the specimen at a lower temperature using a lower laser pulse energy as possible. And also, when you prepare the sample, it's preferred to have a larger shank angle, or no, the larger tip at the bottom that give enough heat dissipation to improve the mass roving power in the laser pulsing mode. Of course, in voltage pulsing mode will be different, and the mass roving power is usually worse than the laser pulsing mode because of the duration of the pulse of the voltage pulsing is wider. And also, even use the laser pulsing mode, if you don't use the adequate condition, like use extensively high laser pulse energy, that may cause thermal tail that degrade the mass roving power. So first of all, you need to collect data as the best quality to avoid overlapping by improving the mass roving power. But again, even though the LEAP we have 6000 XR has a typical mass roving power between 1000 to 1500, that is usually enough to distinguish the difference at 0.1 Dalton. But for difference lower than 0.05 Dalton, it's very hard to distinguish. For example, the overlap between doubly charged silicon at 28 has the difference between nitrogen, singly charged nitrogen at a difference of 0.02 Dalton. That is beyond the resolution mass roving power for the time of flight mass spectrum to resolve. So in that case, you can sometimes you can realize on the non-overlapping peaks with the non-isotopic abundance. So you can mathematically decompose the peak and to calculate how much of the ions can be associated with one ion instead of another element. So my suggestion will be first try to improve your mass roving power as much as possible, and use peak decomposition for more accurate compositional measurement.
Great. So, few structural questions here. Let's see. So, the first one is, can you use Atom Probe Tomography to find defects in crystal structures? And so I'll expand on that a little bit to include a couple other questions that came in. So specifically for like looking at vacancies, for instance. And then after that, some questions about whether you can actually measure hydrogen and carbon reliably with APT.
Oh, yes. So Atom Probe data acquired from pure or close to pure metallic sample contains some degree of crystallography information, but usually the Atom Probe data itself is not enough to determine the type of crystals or the orientation. Orientations, yes, but the type of crystalline structure is not sufficient. So that's why it's usually recommended to combine Atom Probe with TM. That's why we put a lot of efforts in the correlative analysis with TM. And about dislocation or defects or vacancies, so Atom Probe can see some of the hints in the heat map, but the information again, if the defects or dislocation are not associated with segregation, the Atom Probe will be challenging to detect them. The way to see defects or grain boundaries or point defects in Atom Probe is they have to be associated with sort of segregation, like the previous example we had with the magnesium diffusion along the dislocation core. So I assume if the dislocation is there, we can see the V defect, but we won't be able to see the linear dislocation if it doesn't contain segregation behavior. And moving to the hydrogen analysis, all the analysis, Atom Probe analysis contains hydrogen peak at 1 Dalton or 2 Dalton, and some of them may even contain hydrides. So it can sort of qualitatively measure hydrogen, but the difficulty is for every specimen we observe hydrogen that could be contributed by the residue gas in the ultra high vacuum. So it need to put a lot of efforts to know the condition or having a reference material, know how much of the hydrogen are contributed by the background in the vacuum. And also for certain applications, you need to use cryo sample preparation to lock or to lock or to the hydrogen in some of the defects. Otherwise, the hydrogen may diffuse out or move away from the defects. And the carbon for usually we can achieve a good measurement for carbon, but there are also some considerations like detector pile up or multi-heats, lots of ion counts in the multi-heats. So there's a lot of considerations for light elements measurements too. So if you have, I will reply that question in separate email.
Yeah. So one last question here is, are there any memory effects in terms of matrix contamination? I think this might be related to like SIMS related measurements. So is there a difference in the directionality of doing the APT experiment in terms of, driving some constituent in like we see with SIMS, or is APT fairly free of this artifact?
It's not completely free. Like just take example of the carbon in silicon or steel. So the carbon will have a higher field, so it's more difficult to evaporate comparing to the matrix. So that will cause surface retention. So if the analysis is carried out at a relatively low relatively low field, means higher laser pulse energy, then if you see the carbon or other elements that seeing lower in the structure due to the surface retention, and also they may migrate on the surface to the high field poles if the condition is too warm, meaning running specimen at too high laser pulse energy and too high base temperature. So it's not completely free, but so you need to be be careful about using the optimized or appropriate conditions to minimize that effect.
Great. Well, I think with that, we'll finish up here, and for sure, keep your questions coming if you have them, and we'll answer them offline afterwards. And we really appreciate your attending today's webinar. So why choose Eurofins AG? There are several reasons, but I think it's important to state right at the top that client confidentiality is core to our business. We're a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. At EAG, we have various certifications, accreditations, regulatory approvals, and/or licenses to support our clients' different needs. we can help solve your material and engineering related product problems. Thank you so much for attending today and all of your great questions. Back to you, Rena.
Thank you to all of our experts for this robust discussion and presentation. And thank you everyone for attending today's event. If we didn't get to your questions today, we will be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. That is customerservice@me.eurofinsus.com. Also want to mention that I've added a few links to our resources in the chat window, so please check those out. And once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. On behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today, and have a great rest of your day.